Okay, good day. For today, you will learn how to analyze and solve a variety of problems, such as how to find the least expensive route of travel on a vacation, how to determine the most efficient order in which to run errands, and how to schedule meetings at a conference so that no one has two required meetings at the same time. Okay, so for today, we're going to have the discussion about the mathematics of graphs. Okay, this is the last unit that we're going to discuss. Alright, but before we proceed with the formal discussion, I have this one question. Okay, it's about the question of the mayor of the Königsberg during the 18th century, and it's known as the Seven Bridges of Königsberg. Okay, so draw a pathway that would lead a person across each bridge and return him to the starting point without traversing the same bridge twice. Okay, our question here is there a way to visit each landmass using a bridge only once and beginning and arriving at the same point? So let's say we have here four landmasses here, and we have seven bridges. Okay, all you need to do is to traverse all the bridges once, and then you will return to your starting landmass. So is that possible? Okay, so you can pause the video and then try. You can use your pencil and paper to uh, determine if it is possible or not. Okay, so the methods we will use to study these problems can be traced back to an old recreational puzzle presented by the mayor of the Königsberg, or known as the Kaliningrad, in the modern days of here in Russia. In the early 18th century, the Pregel River in a city called the Königsberg surrounded an island before splitting into two. Seven bridges crossed the river and connected four different land areas, similar to the map drawn here. Okay, so many citizens of the time attempted to take a stroll that would lead them across each bridge and return them to starting point without traversing the same bridge twice. But the answer here is none of them could do it. No matter where they chose to start, try it for yourself and let's see. Okay? Try it for yourself and let's see if it is possible. Okay, so actually it's impossible. Okay, in 1736, the Swiss mathematician Leonard Euler proved that it is in fact impossible. Okay, it's impossible to walk such a path. His analysis of the challenge led to the groundwork for a branch of mathematics known as the graph theory or the geometry of position. So later, let's try to discuss how did Leonard Euler answer the question of the mayor. Okay, so he used the concept of the graph theory or the geometry of position. Uh, now, let's try to define. Okay, let's try to identify what is graph theory or the mathematics of graphs. Okay, the graph theory or the mathematics of graphs is a branch of mathematics that illustrates and analyzes connections. Think of all the various connections we experience in our lives. Friends are connected on Facebook, Instagram, and other social media platforms. Cities are connected by roads. Computers are connected across the internet. A branch of mathematics called as the graph theory illustrates and analyzes connections such as those situations. Okay, so it is a set of points called vertices and the line segments or curves called edges that connect vertices. Okay, so here, our in our topic for today, we're going to have the concept of the mathematics of graphs that can be applied to different real life situation. Okay, so now I'll give you an example of a graph. Okay, the first one here is null graph or disconnected graph. So as you can see, there's no connection. There's no connections when it comes to the different dots. Okay, when it comes to different dots. So there are no edges involved here. While in the second example, we have here the connected graph that has a pair of multiple edges. So as you can see, there's connection between each of the vertices that we have here. Okay, each of the vertex that we have in this graph. And then for the third one, it is not connected in a way that it consists of two different sections. Okay, it consists of two different sections. So as you can see, this first one is not connected to another graph. Okay, it's a separate. Okay, they are not connected. So it also contains a loop, as you can see here. And then for the last one, we have connected graph or complete graph. A complete graph has n vertices, then each vertex has a degree of n minus 1. So meaning it's connected. For instance, we have here 5 vertices here, and then it is connected to n minus 1, where n is the number of vertex. So that's 4. It's connected to the other 4 vertex. Okay, so all of them, they are connected to each other. They are connected to each other. And we call that as a complete graph. Okay, it's a complete graph. Now, I'll give you a situation, and then let's try to graph it. Okay? The table lists 5 students at a college. An X indicates that the 2 students participate in the same group this semester. So as you can see, we have here 5 students: Matt, Amber, Oscar, Laura, and Kyla. So again, X means that the 2 students participate in the same group this semester. So all we need to do is to represent the 5 students as the 5 vertices in our graph. And then here, X means it's an edge. Okay, connecting Amber and Matt. Matt and Laura for the first row. And then for Amber and Matt again, Amber and Oscar, then Amber and Laura. Okay, so let's try to illustrate the graph of this. Okay, so as you notice here in our graph, we'll have 5. Okay, 5 vertex. Okay, 5 vertices, then all we need to do is to connect them. Okay, all we need to do is to connect them based on the given table from the previous slide. So Matt is connected to Amber, and Matt is also connected to Laura. Okay, and also Amber is connected to Matt, Amber is connected to Oscar, and Amber is connected to Laura. So as you can see here, if there's a connection between the 2 students, you don't need to repeat the edge. You don't need to repeat the edge. Okay? Then we have Oscar to Amber and Oscar to Kyla. So again, you don't need to repeat the edge given that they have connection. Okay? Then Laura is connected to Amber and to Matt, and Kyla is connected to Oscar. Also, here, let's have another example. Okay, so take note, before we proceed to another example, take note that here, it's your decision where you will locate all the vertex. It could be horizontal, vertical, diagonal, star. It depends on you. It depends on you. And when it comes to the edges, you can use straight line, a curved line, and so on. Okay, it depends on you. So later, let's try to discuss about that. Okay. Given this, let's try to have some questions about the situation. Let's say, which student is involved in the most study groups with others? Based on this graph, which student is involved in the most study groups with the others? Okay, here, Amber. Okay, Amber is connected to more edges than the others, so she is involved with more study groups, which is 3. Okay, to Math, Laura, and to Oscar. How about the student who has only one study group in common with the others? So in this case, we have Kayla. Okay, we have Kayla. Kayla is one of the only student with one study group in common. Okay, as her vertex is only connected to Oscar. Okay, so as you can see, we can analyze, we can interpret the graph as long as we know the situation. Okay, as long as we know the situation of this graph. Another example. The table lists 5 mobile phone companies and indicates whether they have agreements to roam onto each other's networks. So, if no, they are not connected, we're not going to use an edge to connect the two networks. If yes, we're going to connect them. Okay, so look at this. Remember this table, and let's try to present its graph. Okay, so again, all you need to do is to set up all the networks as the 5 vertices in our graph, and take note that they are connected if there's a yes in their cell. Okay, so smart to TNT, smart to sun, and then we have globe to TM and TNT to TM, then TNT to sun, and as you can see, this is now the graph of our situation. So again, you don't need to repeat. The graph or the edges rather when it comes to its connections. Okay, so again, this is the graph of our situation earlier. Now, I told you earlier that we can have different uh, graphs when it comes to arrangement of our vertices and the length of our edges, because we have this concept called as the equivalent graphs, where two graphs are said to be equivalent graphs if the edges form the same connections of vertices in its graph. Okay, so for instance, look at this. Okay, we have three different graphs, but actually they are equivalent graphs. Okay, they have different locations of each vertex, and also they have different lengths of their edges, but they are equivalent. Okay, note that it doesn't matter whether the edges are drawn straight or curved, and their lengths and positions are not important, nor is the exact placement of the vertices important. So as you can see here with the first graph here, we have 5 vertices A, B, C, D, E, and as you can see, B is connected to all the other vertex. So B is connected to A, B is connected to C, B is connected to D, and B is connected to E. Okay? Same goes with the second graph. So as you can see here, we have 5 vertices, A, B, C, D, and E, and B is connected to all the edges, to all the vertex A, C, D, and E. Okay, so as you notice, they only have 4 edges. Okay, and look at this one. Look at the third one. Okay, the third one here is, again, an equivalent graphs. So as you can see, we have again 5 edges, 5 vertex and 4 edges. And B is connected to A, B is connected to C, B is connected to D, and B is connected to E. So as you notice, they have the same connections. They are different graphs when it comes to the location of their vertex and when it comes to the length of their edges, but the connections are still the same. So therefore, they are equivalent graphs. Now, let's try to identify whether the two graphs are equivalent or not. So look at this. Okay, let's start here with the first two graphs in the first row. Are they equivalent graphs? Okay, the answer here is no. Why? Because they don't have same connections. For instance, look at this B and E edge. Okay? So as you can see, in the first graph, they are connected, but look at this. It's not connected. B is not connected to E. So therefore, it's not an equivalent graphs. Okay, it's not equivalent graphs. Okay? And as you notice here, we have B connected to D, while here, it's not connected. They are not connected. Okay, so remember, okay, when it comes to equivalent graphs, all connections should be the same. Okay, take note of that. How about this one? Look at these two graphs below. Okay, look at these two graphs. Are they equivalent graphs? Okay, the answer here is yes. Okay, the answer here is yes. Okay, look at this. The first graph form a square for its vertices, while here it's in horizontal. But if we look at this, they have the same connections. Okay, they have the same connections, such as A is connected to B and connected to D. Same goes here, connected to B, connected to D. Then we have B connected to A, connected to D, connected to C. B is connected to A, to C, and to D. Then for C, it's connected to B, connected to D. And for the second graph, C is connected to B and connected to D. Lastly, D is connected to C, to B, and to A. Same goes here with the second graph. We have D is connected to C, connected to B, and connected to A. Okay, so therefore this one are equivalent graphs. Okay, they are equivalent graphs. Now, in our situation earlier, we can present the seven bridges of Königsberg as in terms of graph. In terms of graph, the original problem can be stated as follows. Okay, we can say, can we start at a vertex, at any vertex, move through each edge once, but no more than once, and return to the same or to the starting vertex. Okay, so let's say if we start with vertex A, we traverse all the bridges once, can we go back to bridge A, to the landmass A? Okay, or if we start with landmass B and we traverse all the edges once, can we go back to landmass B? Same goes with C or with D. So as you can see, we can transform this problem into a graph. Okay, into a graph. Okay, so let's try to answer based on the generalization of Euler. Okay, so by the definition or by the concept that is presented by Leonhard Euler, we have a concept called as the path and a circuit. Okay, we have path and a circuit. A path is a movement from one vertex to another by traversing edges. Okay, so it's just a movement from a certain vertex. You traverse the edges. It's called a path. Okay, but with the subset of path, we have the circuit, or known as the closed path, a path that ends at the same vertex which it started. So let's say you start at vertex A, you should end up with vertex A. You start with vertex B, you should end up with vertex B. For instance, okay, we have here, let's say we start at A, then going to D, F, G, E, B, then go back to A. So this one is a circuit. Okay, this one is a circuit or is a closed path. You started with A, you end up with A. Another example, but it's not a circuit. A going to D, going to F, going to G, going to E, and then end up with H. So this one is not a circuit, but a path. Okay, it's a path, but it's not a circuit. Now, Euler circuit. Okay, so Euler uh, use the situation or use the question of the mayor to have this concept. Okay, the concept of Euler circuit. A circuit that uses every edge but never uses the same edge twice. So as you can see here, you started with a certain vertex, you end up with that vertex, and you use that edge, all the edges, once. Okay, for instance, let's have here this graph. So we have B going to D, going to F, going to G, H, E, C, B, A, D, G, E, then B. So as you can see here, it's an Euler circuit. Okay, you started with B, you end up with B, and you traverse or you visit the edges here once. Okay, so let's have an example that is not an Euler circuit. For instance, we have here A going to B, C, E, H, G, E, B, D, then you end up with A. So as you notice here, not all edges get visited. Okay, so as you can see, we have DF, edges DF, edges FG, and GD. Okay, so as you notice, we should visit all. Okay, we should visit all the edges. Okay, we should visit it once. Another example, we have A going to B, going to C, going to E, H, G, F, D, A, B, E, G, D, and then you end up with A. So as you notice here, the path did not visit the edges BD, the edge BD. And also it repeats the visit to edges AD and AB. Okay, so therefore, this is not an Euler circuit. Okay, that is not an Euler circuit. So, Euler try to generalize the concept wherein you can identify whether the graph is having an Euler circuit or not. Okay, so by the definition, Euler circuit, it uses every edge but never uses the same edge twice. And by the definition, it's a connected graph has an Euler circuit if and only if every vertex of the graph is of even degree. Okay, every vertex of the graph is of even degree. Okay, now, what is even degree? Okay, so degree means is the number of connection of each vertex or the number of edges on each vertex. Okay, for instance, let's identify whether this graph has an Euler circuit or not. Okay, so all we need to do is to identify the number of edges connected to each vertex. Okay, that is called as the degree. Okay, for instance, A is connected to B, connected to E. So as you notice, we have the degree of 2. Then B is connected to A, connected to E, connected to D, and connected to C. We have the degree of 4. So 4 connections. E is connected to A, connected to B, connected to C, and connected to D. So we have another 4 connections, so degree of 4. Then C is connected to B, connected to E, and then connected to D. So we have the degree of 3 connections. D is connected to C, connected to B, and connected to E. So there are 3 connections. So as you notice, we have the degree of 2 for vertex A, and then vertex B, vertex E, with the degree of 4, vertex C and D with the degree of 3. So now, by basing our answer from the definition from the generalization of Euler, this graph has no Euler circuit. Okay, so as you notice here, we have even degree for A, B, and E vertex, but for vertices C and D, they are odd. 3 is odd number. So therefore, this graph has no Euler circuit. Okay, it has no Euler circuit. Another example. Okay, we have here the star. Okay, we have here the star with the vertices A, B, C, D, and E with its connection. So try to identify if this graph has an Euler circuit. Okay, so as you can see here, each vertex has a degree of 2, right? There are 2 connections on each vertex. So if that's the case, 2 is even, and all of the vertex here have a degree of 2. Okay, so therefore, this graph has an Euler circuit. This graph has an Euler circuit. So if you will remember, if you're going to draw a star without lifting your pen, you can do that, right? So you can do that. So let's say you start with vertex A, going to C, going to E, going to B, D, and then you end up with A. Okay, so as you notice, you can draw a star without lifting your pen. Okay, you start with A, then you end up with A. Okay, it's the same with starting with B, C, D, or to vertex E. Another example. Okay, so earlier we have the 7 bridges of Königsberg, and we have its graph. So let's try to identify, based on the definition of Euler circuit, okay, is this possible? Does it have an Euler circuit? Earlier, we have our answer that it's impossible to take a stroll starting at a certain landmass and you traverse the bridge once, you end up with that landmass. It's impossible. Actually, it follows also the definition of Euler. So as you notice here, we have A has a degree of 5. So we have 5 bridges connected to A, or landmass A. Right? So here we have the degree of 5. For B and C, B and C, that is 3. We have 3 connections or 3 bridges connected to them. And same goes with D. It has 3 bridges connected to them. Okay, so all of the vertex here have a degree of an odd, okay, an odd number. So if that's the case, it's impossible. Okay, it's no Euler circuit, and it's impossible with our question earlier, with the question of our mayor earlier. Okay, there's no Euler circuit here, and it's impossible that you visit each landmass using a bridge only once and beginning and arriving at the same point. Okay, that's impossible because all of the vertex here has uh, odd, okay, odd degree. Okay, now how about this one? Try to identify if the given graph has an Euler circuit. If the given graph has an Euler circuit. So you can pause for you to count the number of edges connected to each vertex. Okay, so as you can see here, we have for vertex A, that's degree of 2, vertex B, degree of 6, vertex C, that's degree of 2, vertex D, degree of 4, vertex E, F, and G, also degree of 4. So as you can see, as you notice, we have an even degree for all the vertices here. So therefore, it has an Euler circuit. Okay, it has an Euler circuit. So I'll give you an example. Okay, so let's start with B, going to A, going to F, then go back to B, E, F, G, E, D, G, B, D, C, and then you end up with B. So as you can see, this graph has an Euler circuit. Now, let's try. Let's say we try to revise the map. We try to revise the geographical uh, representation of the uh, Königsberg Bridge. Let's say we have this. Let's say we have this. Would the citizens be able to complete a stroll across each bridge and return to their starting points without crossing the same bridge twice? Okay, so in this case, is it possible? Is it possible? Okay, the answer here is yes, it's possible. Because if we're going to look at each landmass, it has a degree of 4. Okay, there are 4 bridges connected to that. Okay, so as you can see here with this landmass, it has 4 bridges connected to this. And then also this one, 4 bridges. Okay, then landmass here, we have 4 bridges again. And then landmass here below, we have again 4 connections or 4 bridges. So each landmass, each vertex has a degree of 4. So therefore, it's even and it has an Euler circuit. So it's possible. Again, it's possible to take a stroll. Okay, and you visit each landmass, traversing the bridges once. Okay, it's possible. Okay. In addition, okay, with the concept of Euler circuit, we have the definition of Euler path. Okay, Euler path theorem. So, Euler path is a connected graph contains with this condition two vertices of odd degree with all other vertices of even degree. And furthermore, every Euler path must start at one of the vertices of odd degree and end at the other. So take note, two vertices of odd degree and the rest is even. Okay, then you're going to start at one of the vertices of odd degree and end up with the other odd degree. Okay? So if a graph is connected and has a 0 or exactly two vertices of odd degree, then it has an Euler path. Okay, it has at least one Euler path. Every Euler circuit is an Euler path, but not every Euler path is an Euler circuit. Earlier we have this example. Okay, earlier we have this example. Uh, let's try to identify if there's an Euler path this time. Okay, so there's no Euler circuit here, but maybe there's an Euler path here. So earlier, we identified the degree, okay, of each vertex. Okay, so in this case, as you look at this, we have vertex C and D with odd degree, and by the definition of Euler path, you should have this two odd degree and the rest is even. So in this case, it has an Euler path. Okay, so let's say we start with vertex C, going to vertex B, A, E, D, B, E, C, and then you end up with D. You end up with D. So we started with vertex C, you end up with vertex D. Or vice versa, you start with vertex D, then you end up with vertex C. So take note, you should start and end at the odd degree vertex. Okay, you should start and end at the odd degree vertex. Now, let's have this art gallery floor plan. Okay, let's have this situation. The floor plan of an art gallery is pictured here. So let's try to draw a graph that represents the floor plan, where vertices corresponds to the rooms and edges corresponds to the doorways. Okay, and we have the questions here. Is it possible to take a stroll that passes through every doorway without going through the same doorway twice? If so, does it matter whether we return to the starting point? Okay, so in this case, again, we're going to represent each rooms as vertex, each room as vertex, and the doorways as the edges. Let's consider the degree of each vertex. So let's say we have here for vertex A, we have the degree of 2. So there are 2 doorways. Then B, we have 1, 2, 3, and 4. So 4 doorways, so degree of 4. C, 1, 2, and 3. So 3 doorways, so degree of 3. D, 1, 2, and 3. So again, we have 3. Then for vertex E, we have 1 and 2. So degree of 2. And then for vertex F, we have 6. 1, 2, 3, 4, 5, and 6. Okay, now, let's try to answer the questions here. But to answer the question here, we need to identify if it is under the Euler circuit, the Euler path, or neither. Okay, look at this. Let's try to identify the degree of each vertex. If we have this degree of vertex, it's impossible to have an Euler circuit. Right? It is not an Euler circuit because we have the degree of odd with vertex C and vertex D. Degree of 3. But if we're going to consider, we're going to look at this, it could be an Euler path. Right? There's an Euler path here because we have vertex C and vertex D with odd degree and the rest is even. So in this case, we can say that it's possible to have an Euler path. Okay, so let's say we started with C, we end up with D, or vice versa. So let's say we have C going to B, going to F, going to be again A, F, E, D, C, F, then you end up with D. Okay, so as you can see here, Euler path exists. Okay, it exists. Okay, so we have, you started with C, you end up with D, or vice versa. You started with D, you end up with C. Okay, so to answer the question, is it possible to take a stroll that passes through every doorway without going through the same doorway twice? Yes, it's possible. Yeah, yes, it's possible. So based on this, it's possible, and based on the definition of Euler path, it's possible. If so, does it matter whether we return to the starting point? So the answer here is no. Okay, because look at this. Look at this. We started with vertex C, then we end up with vertex D. Okay, so in this case, it has an Euler path, so therefore, it's not possible. It's not possible that you start with vertex C, then you end up with vertex C. Okay, so you will start with vertex with an odd degree, you end up with the other. Okay, that's an Euler path. Okay, so remember that again, when it comes to Euler path, it has two vertices with odd degree. Okay, so later for part 2, let's try to have the Hamiltonian circuit and Hamiltonian path.